Alright, so in this video we are going to talk about a very important concept, and this concept we often need when we try to initiate our condensed matter research. We often are supposed to do some finite size calculation when the system, we suppose we take some finite lattice size and then do our calculation. So for that kind of calculation, what approach is to be taken, that we are going to discuss. And for this particular example we are going to talk about a 4x4 size lattice, and with that we will learn how to do this finite size calculation in condensed matter, and later also we'll see some part of code how to form the matrix using this method. Okay, so suppose you have a 4x4 lattice, so that will look something like this there these are, as you can see, there are 16 lattice sides beginning from 1 1 and ending to 4 4. So 1 1 1 2 1 3 1 4, 2 1 2 2 2 3 2 4, 3 1 3 2 3 3 3 4, 4 1 4 2 4 3 4 4, each are a particular lattice size. So at each site you can think that there is electron and which can hop to the nearest neighbors. So what does this nearest neighbor means? So suppose you take the electron at a particular site 1 1, then it can go to 1 2 or 2 1, and also it can go to 4 1. 1 1 can go to 4 1 and also 1 4 because of the periodic boundary condition. So periodic boundary condition you can think of like a water flowing. So if the water is flowing out of this 1 1 site, it is supposed to enter through 1 4 site, and if the water is going like a negative y direction, and then it is supposed to come in from the 4 1 site. And if you take any point in the middle of the lattice like 3 2, so you can easily understand from 3 2 the electron can go to 3 1 or 3 3 or 2 2 or 4 2, only these four nearest neighbors. So each site has four nearest neighbors. Okay, so this is the hopping mechanism that is going to happen on this particular lattice. So electrons can hop like this. Okay, so for this kind of scenario, how do we form the matrix for the system? So I am not using any particular kind of Hamiltonian to represent here. I am just trying to give you an idea of the mathematics behind it. So try to just picturize inside of your mind, and in that way you will be able to understand better. So like I said, hopping can be done like from 1 2 to 2 2, you can see in the right hand picture, then 1 1 to 2 1, and also the Hermitian conjugate terms are also allowed. So hopping from 1 2 to 1 1 or 2 1 to 1 1 is also allowed. And for the boundary cases, like you can see, from 1 1 to 1 4 or 1 4 to 1 1 is allowed, and then 4 1 to 4 4, then 4 4 to 4 1 is again allowed. So what happens, you can notice for 2 1 or 3 1, this kind of elements, so they are already in the lattice. In this kind of structure there are three nearest neighbors, like 3 1 have 2 1, 3 2 and 4 1. But for the when a particle electron can want to hop from 3 1 to the left hand side, then it will go to the 3 4 side because of this periodic boundary condition. All right, so that's how this hopping happens in here. I think the picture is pretty clear because it's not much complicated. Okay, so to form the matrix, so we'll need to write down the Hamiltonian in terms of C and C dagger, as you know. So C, if you consider the C dagger creates a particle, so C means that it annihilates a particle. So in terms of, you can think like a particle and antiparticle. So just think like C dagger is a particle and C is an antiparticle. And also there can be two spins available, so like up spin or down spin. So one important thing to notice in here is, for a particular site there can be four possible values for this C, and these are C up, C dagger up, C down or C dagger down for any particular site. Suppose 1 1 or 2 2, 2 3, 2 4, 3 4, 3 3, doesn't matter, any site. The electron can be any of these four states. So the matrix should be 4 cross 4 for this 4 cross 4 lattice. Okay, for not because of this 4 cross 4 lattice, this is 4 cross 4 because there are four kind of available combination is available, because on two due to spin and two due to particle and antiparticle. That's why it's 4 cross 4. But important thing to notice in here is each of this block, that I have written in here, I have drawn in here, like each of these blocks again will contain, so how many elements each of these blocks will contain. So now consider this for this, so if there can be 4 possibilities at each side, so there are 16 sides. So oh sorry, it went from here, okay, yeah, so it can be, there can be 16 sides, so there can be 16 C up, there can be 16 C dagger up, there can be 16 C down, and there can be 16 C dagger down. So total size of this whole matrix will be 64 by 64. So each of these blocks again will be 16 cross 16. Okay, so there are 4 blocks, so it will be 16 into 4 in the rows and 16 into 4 in the columns. So there will be 64 by 64 for a 4 cross 4 lattice which has 16 sides, because each side can have 4 different possible states. Okay, so if this is clear, then next we will move to the code and we will see how to form this matrix. We will use the Python language and we will see how to form this matrix using like in 2D. So one possible way of doing this, forming this matrix, is using mapping this 2D matrix, like this 2D, two variables are there, like 1 1 1 2 and 2 1 2 2, so 2 variables are there, so map them to some 1D case and then form a 64. So in that case it will be, you can then form the 64 by 64 matrix, but it will be, that will be a bit clumsy, but we will see in Python how we will do it using 2 variables, like two matrix variables. Okay, so for that part we will move to the code. Okay, all right, so as you can see, so here I have written the code for this, and I want to explain what I have done in here. So like it is written, this is to form the complete matrix for n cross n. Here it will be like 64 by 6 feet, considering particle and antiparticle and up and down spin, like the 4 variables we have already talked about. And so here we will only give input as the dimension. This dimension means what is the dimension of the lattice size, not the matrix size. So we'll just put the dimension of the lattice size, like here in case we are considering 4 cross 4 matrix, 4 cross 4 lattice. So that will input and automatically we will get a 64 by 64 matrix. So only you need to give the dimension of the lattice. So suppose you can go to any number, you can go to 1000, 1 lakh, 1 billion, it doesn't matter. It is supposed to give you the corresponding matrix. So for a 4 cross 4 it will be 64 by 64, but for if you give a 1 million it will be much bigger, and it will be like 16 times of that. Okay, 16 times of 1. So if you give 1 million it will be 16 million, the matrix size will be 16 million, right? 16 million by 16 million, so it will be huge, and that will take a huge number of time to calculate. So for that is a different issue, how do you tackle that problem, but for now we'll see how to form this matrix. So like we said, so there will be bunch of logic that we will define. That logic is given in here to forming the different those blocks that I have shown earlier, those blocks of the matrix. So here I have first I am taking this S1 as the 1 spin, and under that PA as the particle, and then under that suppose I and J is the, suppose it will, I and J will give you the number of rows. If I and J varies, the rows varies. And within that, so here I have defining one empty list, and then within that I am defining another empty list. For that another spin, so this spin is the other spin, it can be up and down, anything. This antiparticle, if this is particle, so then we will take this as antiparticle, and with if then under that K and L, that will decide the row elements. So first what will happen when this 4 loops runs in this A empty list, you will for a fixed particular row, because row is varying in this upper loop, so for a fixed particular row we will get all the column elements. And then when this upper loops varies, then this again you will get more subsequent rows, and eventually we will get the whole matrix as an array. Okay, so that is the logic behind using this 2D. This is how we can form a 2D matrix. Okay, just try to just try to picturize it in your head, otherwise it can be a little bit difficult to understand. So this upper loop is for the varying rows. This down loop is, these down four loops are varying the columns. And so this dimension is 4 cross 4. So four dimension is 4, and again there will be two variation for this. Like, so you can think like this two can be up and down, and this two can be C and C dagger. So, and this dimension is 4, so you can think like this corresponds to a C up, C dagger up, C down, C dagger down. Similarly, this 4 also corresponds to this C up, C dagger up, C down, C dagger down, but in some different order. And here comes the logic. So logic for the disorder potential part, like if the matrix has some potential part, suppose there is some interaction potential is there, which is like acts like a disorder in the system, and they are only in the diagonal elements. They sit only in the diagonal elements. So for that we have defined this kind of logics, like I minus k has to be 0, because suppose there is a one element like C11 and C11. So for all these diagonal elements, always the I and j, this I and this k and j and l will be 0. The spins should also be 0. Actually, these conditions can vary depending upon your interaction and how your Hamiltonian is given, but the key part is here to notice this, that I earlier said about these two loops. This actually total 8 loops, but four of loops up in two sets, and that's how you can form a 2D matrix. It's very important because not many people know this thing. So, and these conditions will vary upon your on your system Hamiltonian which is given. So for this kind of particular system, it was this disorder potential was there, and they were at the diagonal element, and this off diagonal elements was like C dagger C, then C dagger C, and then C dagger C dagger C for suppose for up. Okay, and this maybe for down, like that I have defined, and there was some superconducting interaction was also there, for that also I have defined. So this part I can maybe discuss in some later videos. For this video it's not important because it's specific to the particular problem really, and it's more in depth who are doing the research. For them I may maybe talk about this in some later videos. So for now I think this is sufficient, and if you have any doubt, make sure that you comment down, and I will try to clarify those confusions that you have. I'm sorry, actually I have not for this coding part I have not really drawing or doing any explanation like that, so you have to little bit work with your own brain to get it. I hope you can get that. Okay, thank you.